In this lesson, we will focus on an important aspect of drilling, reaming, and boring techniques and tool applications in Project 1 drilling quality analysis and control. We will delve into various factors affecting drilling quality, such as the geometry of the drill bit and cutting parameters. Additionally, we will learn how to control these factors to ensure the quality of the drilling process. By acquiring this knowledge, you will be better equipped to master drilling techniques, laying a solid foundation for practical production operations. In metal cutting processes, drilling is a common and important machining method. It is widely used in various fields, such as mechanical manufacturing, aerospace, and automotive industry. For example, in the manufacturing process of automobile engines, various holes of different sizes and depths need to be drilled into the engine block for the installation of components such as pistons and valves. The quality of these holes directly affects the performance and the reliability of the engine. Key indicators of drilling quality. Drilling quality is primarily measured by several indicators, including dimensional accuracy, shape accuracy, surface roughness, and positional accuracy. Dimensional accuracy. This refers to the degree to which the dimensions of the drilled hole, such as diameter and depth, conform to design specifications. For instance, in the manufacturing of precision molds, the diameter tolerance of a hole may be required to be controlled within plus or minus 0.01 mm. If the dimensional accuracy does not meet the standards, it may result in parts not fitting properly, thereby affecting the performance of the entire product. Shape accuracy. This primarily includes roundness and cylindricity. Roundness refers to the degree to which the cross-section of the hole approaches a perfect circle, while cylindricity pertains to the straightness of the hole's axis and the shape error of the cylindrical surface. Poor shape accuracy can affect the fitting precision and the motion accuracy of parts. Surface roughness. This reflects the macroscopic unevenness of the hole wall surface. Appropriate surface roughness can ensure the wear resistance, corrosion resistance, and the sealing capability of the parts. For example, in hydraulic systems, the surface roughness of a hole significantly affects sealing performance. If the surface is too rough, it may lead to hydraulic oil leakage. Positional accuracy. This refers to the accuracy of the hole's axis in relation to other surfaces or holes. It is typically measured by indicators such as position tolerance, coaxiality, and parallelism. During assembly, the positional accuracy of holes directly affects the assembly relationship and motion accuracy between parts. Factors affecting drilling quality. The geometry of the drill bit significantly impacts the quality of drilling. A common type of drill bit is the twist drill, whose main geometric parameters include the point angle, relief angle, and chisel edge angle. Point angle. The point angle is the angle between the two main cutting edges as projected onto a plane parallel to the drill bit's axis. The size of the point angle affects the cutting force and chip removal performance of the drill bit. Generally speaking, the smaller the point angle, the sharper the cutting edge of the drill bit, resulting in lower cutting force, but with relatively less space for chip removal. Conversely, a larger point angle provides more space for chip removal, but the cutting force will also increase accordingly. For example, when machining materials with higher hardness, the point angle can be appropriately increased to enhance the strength and durability of the drill bit. Relief angle. The relief angle is the angle between the main flank surface and the cutting plane. Its function is to reduce friction between the flank surface of the drill bit and the hole wall. If the relief angle is too large, the strength of the drill bit's cutting edge will decrease. If the relief angle is too small, friction will increase, affecting both the quality of the drilling and the lifespan of the drill bit. Chisel edge angle. The chisel edge angle is the angle between the chisel edge and the main cutting edge as projected onto a plane, perpendicular to the drill bit's axis. The size of the chisel edge angle affects the length and sharpness of the chisel edge. An appropriate chisel edge angle can reduce axial force and improve the stability of the drilling process. Cutting parameters. Cutting parameters mainly include cutting speed, feed rate, and the depth of cut. Cutting speed. Cutting speed refers to the linear velocity of a point on the cutting edge of the drill bit relative to the workpiece's primary motion. The formula for calculating cutting speed is Vc equals pi times dw times n divided by 1000, where d is the drill bit diameter in millimeter, and n is the drill bit's rotational speed in revolutions per minute. If the cutting speed is too high, it can lead to increased wear on the drill bit and even cause burning. Conversely, if the cutting speed is too low, it will reduce production efficiency. Feed rate. The feed rate, denoted as F, refers to the axial distance the drill bit moves relative to the workpiece per revolution, rev. If the feed rate is too large, it will increase the cutting force and worsen the surface roughness of the hole. If the feed rate is too small, it will reduce production efficiency. Depth of cut. The depth of cut, denoted as AP, refers to the thickness of the metal layer removed by the drill bit in a single feed. For drilling operations, the depth of cut is equal to half the diameter of the drill bit. AP equals D divided by 2. The size of the depth of cut directly affects the cutting force and cutting power. Workpiece material. Different workpiece materials have varying mechanical properties and machining characteristics, which significantly impact drilling quality. For example, aluminum alloys are relatively soft, and during drilling, they are prone to causing chip adhesion, affecting the surface quality of the hole. In contrast, stainless steel has higher toughness and strength, resulting in greater cutting forces, faster drill bit wear, and a tendency for work hardening, which affects the dimensional accuracy and surface roughness of the drilled hole. Rigidity of the machining process system. The rigidity of the machining process system includes the rigidity of the machine tool, fixtures, and workpiece. If the process system lacks sufficient rigidity, vibrations may occur during drilling, leading to poor shape accuracy and surface roughness of the hole. For example, when using a small drill press to machine large workpieces, the limited rigidity of the drill press may result in issues with the roundness and the cylindricity of the hole exceeding tolerances. Drilling deflection, issue, and control. Deflection is a common problem in the drilling process. It refers to the deviation of the drill bit's axis from the ideal position as it penetrates the workpiece due to various reasons, thereby affecting the positional accuracy and shape accuracy of the hole. Deflection may be caused by factors such as asymmetrical sharpening of the drill bit, uneven workpiece surface, or unbalanced cutting forces. For example, when drilling thin sheet workpieces, if there are slight protrusions or depressions on the workpiece surface, the drill bit is prone to deflection upon contact. Although deflection may seem like a minor issue, it can have a critical impact on the overall drilling quality. If the positional accuracy of the hole deviates excessively, it may result in parts that cannot be properly assembled or even lead to scrapping, causing resource waste and increased costs. To control drilling deflection, the following measures can be taken. Pre-drilling a centering pit. Before drilling, use a center drill to create a centering pit on the workpiece surface. This provides accurate positioning for the drill bit, reducing the likelihood of deflection. Using a guide bushing. A guide bushing can restrict the movement direction of the drill bit, improving the positional accuracy of the drilling. Guide bushings are typically mounted on fixtures and used in conjunction with the drill bit. Selecting appropriate drill bits and cutting parameters. Choose drill bits with high sharpening precision and good rigidity. Additionally, select cutting parameters based on the workpiece material and machining requirements to reduce unbalanced cutting forces, thereby lowering the risk of deflection. Methods for controlling drilling quality. Tool selection and sharpening. Choosing the appropriate drill bit is crucial for ensuring drilling quality. The type and specifications of the drill bit should be selected based on factors such as the workpiece material, hole size, and precision requirements. Additionally, the sharpening quality of the drill bit must be ensured so that its geometric parameters meet design requirements. For example, for high-precision drilling operations, carbide drill bits can be selected and sharpened using specialized equipment. Optimization of cutting parameters. Based on the workpiece material and drill bit performance, it is important to reasonably select cutting parameters such as cutting speed, feed rate, and the depth of cut. The optimal combination of cutting parameters can be determined through experimentation and the accumulation of experience. For example, when machining high-strength alloy steel, reducing the cutting speed and increasing the feed rate can improve machining efficiency and drilling quality. The use of cutting fluid. Cutting fluid plays a crucial role in the drilling process. It can reduce cutting temperature, decrease tool wear, improve surface quality, and enhance chip removal performance. Common cutting fluids include emulsions and cutting oils. When machining different materials, the appropriate cutting fluid should be selected. For example, when machining aluminum alloys, emulsions can be used as the cutting fluid to enhance cooling and lubrication effects. Monitoring the machining process. During the drilling process, various monitoring methods can be employed, such as measuring cutting force, cutting temperature, and vibration parameters, to promptly detect any abnormalities in the machining process and take appropriate corrective actions. For instance, if the cutting force suddenly increases, it may indicate severe drill bit wear or the occurrence of deflection. In such cases, the drill bit should be replaced, or cutting parameters should be adjusted in a timely manner. From the critical impact of the seemingly minor issue of drilling deflection on overall quality, we can deeply appreciate the importance of craftsmanship. In metal cutting processes, every detail can affect the final product quality. As future engineers and technicians, we must cultivate a spirit of craftsmanship characterized by striving for excellence and meticulousness. We should pay attention to every aspect of our work and not overlook any minor issues. Only in this way can we produce high-quality products and contribute to the development of our country's manufacturing industry. In this lesson, we conducted a detailed study on the analysis and control of drilling quality. We first introduced the important indicators of drilling quality, including dimensional accuracy, shape accuracy, surface roughness, and positional accuracy. Then, we analyzed the factors affecting drilling quality, such as the geometry of the drill bit, cutting parameters, workpiece material, and the rigidity of the machining system. We focused on the issue of drilling deflection and its control methods, as well as the methods for controlling drilling quality, including tool selection and sharpening, optimization of cutting parameters, use of cutting fluids, and monitoring of the machining process. Through learning this knowledge, we should recognize the importance of drilling quality and the spirit of craftsmanship, which emphasizes attention to detail and striving for excellence in the machining process. I hope that in your future studies and work, you will be able to apply the knowledge you have learned to actual production, continuously improving drilling quality and machining efficiency.